Almost every secure connection you make today leans on one lopsided fact. Take two large prime numbers and multiply them, and you get their product in an instant. Now hand someone only that product and ask them to recover the two primes you started from. For a number a few hundred digits long, every classical method we know would run for longer than the age of the universe. Multiplying is easy, factoring back is hard. That gap is the lock. The system called RSA builds the whole edifice of public key cryptography right on top of it.
If factoring is that hard, what could possibly break it?
For decades, nothing did. Then in 1994, a mathematician named Peter Shor, working at Bell Labs, found a way. He wrote down an algorithm that factors a number in polynomial time. Fast, not on a classical computer, but on a quantum one. It is the single result that turned quantum computing from a physicist's curiosity into a field. Before Shor, a quantum computer was an interesting thought experiment. After Shor, it was a machine that could pick the internet's locks, and almost overnight, governments began to pay attention. Here is the uncomfortable part. The algorithm is proven, the mathematics is not in doubt. The only thing standing between us and a broken lock is engineering, a quantum computer big enough to run it. So the encryption guarding secrets today does not have a bug. It has an expiration date. In this episode, we assemble Shor's algorithm from pieces we already have, and watch the number 15 come apart into 3 and 5. The chain begins with a bridge that looks like it has nothing to do with factoring. Pick a whole number smaller than the one you want to factor, sharing no common divisor with it, and call it the symbol A. Now look at its powers, but wrap them around. The symbol A, then A squared, then A cubed, each taken modulo the number you are factoring, so you keep only the remainder. That stream of remainders does something inevitable. It repeats. Sooner or later, A power comes back around to 1, and the whole cycle starts over. The length of that cycle, the smallest number of steps it takes to return to 1, is called the period.
Can we watch that happen on a real number?
Let us factor 15, and take the symbol A to be 7. 7 to the first power is 7. 7 squared is 49, which modulo 15 leaves 4. 7 cubed leaves 13. And 7 to the fourth comes all the way back to 1. 4 steps to close the loop. The period here is 4. Now the old number theory pays off. When the period is even, you can cut the power in half. Half of 4 is 2, and 7 squared modulo 15 is 4. Take the greatest common divisor of that value, minus 1 with 15, and of that value plus 1 with 15. One of them comes out 3, the other comes out 5. The factors of 15 fall straight out, with no quantum computer anywhere in sight.
Then what is left for the quantum computer to do it all?
Everything hard. Finding that period, classically, is exactly as expensive as factoring in the first place. You would have to march through the powers one at a time, and for a number hundreds of digits long, there are astronomically many. The quantum computer has one job, and only one: find the period fast. So we have quietly traded factoring for period finding. And period finding, it turns out, is a question about frequency. A sequence that repeats every 4 steps is, if you squint, a wave. And a wave has a frequency. Look at these amplitude bars. The heights and the little phase arrows trace out a pattern that comes back around every 4 positions, the same rhythm we just saw in the powers of 7. In the previous episode, we built exactly the instrument that reads frequencies out of a quantum state. The quantum Fourier transform, wrapped up as phase estimation. Feed it a pattern that repeats with period 4, and it answers with a spike at the matching frequency. So the plan is to build a quantum state whose hidden rhythm is the period we are after, and let the frequency reader tell us what that rhythm is. To turn the period into a rhythm the machine can feel, we lean on one operator: multiply by the symbol A, modulo n. All it does is shuffle the states around. A permutation, so it is a perfectly legal quantum operation. And because multiplying by the symbol exactly a period's worth of times brings every state home again, the operator's natural phases are forced onto an evenly spaced grid, multiples of 1 divided by the period. Read off one of those phases as a fraction, and the number sitting underneath, the denominator, is the period itself.
But to read a phase, doesn't phase estimation need you to hand it exactly the right state to point at? We don't know those states.
That is the obstacle, and Shor's cleverest move steps right around it. The plainest state of all, the one we simply call 1, turns out to be an equal blend of every one of those special states at once. So we never have to know them. Point phase estimation at the state 1, and it reads back the phase of a random member of the blend, some multiple of 1 over the period. 1 run, 1 fraction, and the period is hiding in the denominator. A single run hands back a number like 0.25 or 0.75. A small classical routine, the continued fraction, turns that decimal back into a clean fraction and reads off its denominator, 4, the period. Why a continued fraction? Because it finds the simplest fraction close to the measured value, and we only allow denominators below the number we are factoring, which is exactly the range the true period lives in. Some runs are simply unlucky. Measure 0.5 and the fraction is 1/2, which suggests a period of 2. But 7 squared is not 1 modulo 15, so that candidate fails the check, and we reject it and run again. A couple of tries is all it ever takes, and each try is cheap.
So all of these pieces really connect end to end.
They do, and it is worth seeing how little code it comes down to. Build the multiply by 7 operator. Run phase estimation on the state 1 to recover the period, 4. Hand that to the classical reduction, and it returns the pair 3 and 5. Factoring reduced to period finding, the period read off as a phase, the phase turned back into a whole number, with the one clever step that the state 1 already contained every eigenstate we needed. We built every piece from a plain array of complex numbers upward, gate by gate, and watched 15 come apart into 3 and 5.
So should I be worried my messages are already being cracked?
Not tonight. The version we just ran is genuinely real, but it is stuck at 15, and the reason is our simulator, not the algorithm. Every qubit we add doubles the size of the array we have to store, so an ordinary laptop runs out of room almost at once. Real RSA keys are numbers over 2,000 bits long. The distance between 15 and that is staggering. To factor a number that big, a quantum computer would need a few thousand nearly perfect qubits. And qubits are not nearly perfect. They leak, they drift, they soak up noise from the world around them. Covering for all of that takes error correction, which spends hundreds or thousands of noisy physical qubits just to fake one reliable one. The true requirement climbs into the millions. That machine does not exist yet, and it may be years or decades away. We will spend the back half of this series on exactly why it is so hard to build. But look at what does not depend on the hardware at all. The algorithm is finished. The proof is airtight. The only missing ingredient is a big enough machine, and machines get built. Which is why encryption protecting a secret today does not have to be broken today to already be in trouble. An adversary can record your traffic now and simply wait, decrypting it the day the machine arrives. That is what an expiration date really means. Somewhere out there is a number that will one day be factored, and the whole world is quietly racing to change the locks before it is. The math already knows how the story ends,